To conclude this lesson, I want to talk about a couple of extensions to the Hough transform, and then some of these extensions are going to carry over both to the next lesson and the one after. By far, sort of the extension that people leverage the most is the one shown here using the gradient. You'll notice that our algorithm is almost exactly the same. We initialize our accumulator array, we iterate over each point, but now instead of looping or iterating over all possible orientations, we actually take the gradient at that point and we take theta from that gradient. Now, you could take a single theta, or you might even take a range of thetas where you say, well, I know that it's approximately 45 degrees plus or minus 10, so I'll vote from minus 35 to 55, but I don't have to worry about voting for all the others. I've written it here as if you got a single value. Now that you have theta, you can solve your equation directly, just as we did before, and we increment our accumulator array. The nice thing is that by using the gradient, you've reduced the voting time hugely, right? You don't have to worry, you just have a single point. Also later you can use it to reduce the dimensionality. So this is the extension that people make use of the most. In fact, the whole notion of orientation is something we'll talk about more going forward. A few other extensions. One is, well, remember when we were doing edge detection, we said that some edges had stronger magnitude than others, and you have to set a threshold. Well, you might lower that threshold a bit to try to get more edges, but the idea is you might want to count the edges with a higher threshold more. Well, what would it mean to count them more? Well, you could imagine that stronger edges would get more votes. Another extension, and this is similar to what I was talking about before, is playing with or changing the bin size of theta and d. As we said before, big bins make it easy to, first of all, vote, it's fast, but you sometimes can get similar lines landing in the same bin. Too fine a bin, and you have this problem that the real line, because of noise, votes for different bins. So extension is to do this hierarchically. First, do a coarse binning where you have sort of larger bins that capture more values. Once you find peaks there, you then go to finer arrays just within those areas, and you improve your recovering of the model. And finally, it's not just an extension, but it's a whole new way of doing things. We did this for lines, but you can do this easily. I shouldn't say easily. You can do this pretty straightforwardly for other parameterized types of shapes, like circles, which in fact we will be doing in a little bit. Oh, and you'll be doing as well. Or actually any other shape, including shapes that are defined by their templates.